These are the frequently asked questions for pre-calculus, and this is for the second day of the test 8.1 to 8.3 review. There were a few questions that were written down because I was gone today that you asked for that are already on another video. So if you were looking for section 8.1, 50, 59, and 60, those, all three of those are already on the FAQ video for section 8.1 day 3. And if you needed from section 8.3, page 609, number 36, that was already on the FAQ video for sections 8.3, day 1. So what I'm going to do now is just cover all the rest of them that were not already something that was listed on another video, rather than re-record the exact same problem that I've done before. All right, so we take a look at this first one. This one came from section 8.1, number 24. It says, find an equation in the standard form for the parabola that satisfies the given conditions. Best thing you can do for these is to make a sketch. It doesn't have to be a Cartesian coordinate plane. Any kind of sketch generally helps you out. So the focus of this parabola is at 2, -3. So there's our focus. And the directrix is the line x equals 5. Now that directrix is important because that directrix is going to tell us which way this parabola is going to open up. Because remember, the directrix is the line that says don't go this way, go the other way. And it also helps us figure out where that vertex is, because that vertex is going to be halfway between our focus at 2, -3 and that line of x equals 5. So what I know about that vertex is it's going to be something -3. And that's because this is going to be a left opening parabola. Wrapping around that focus ensures that. So we've got a left opening parabola. That also ensures that I'm going to need to use y minus k squared equals 4p times the quantity x minus h. Remember, y squared is for right and left opening parabolas. Well, now I need the vertex, and then I need to figure out the value that I should use for p, the directed distance from the focus to the vertex. So the vertex is going to be halfway between 2 and 5. And to find that, you could just take 2 plus 5 and divide it by 2. So that will give you 7/2. So not exactly, pleasant, nice integer there, but they don't always work out that way. So now we know that the vertex is at 7/2 and -3. We also know that our focus was at 2, -3. And to find p, that distance, we need to know how far it is from 2 to 7/2. So 2 would be the same thing as 4/2. So 4/2 minus 7/2 would give us a -3/2. Now the other way to think about that is in terms of decimals. Our 7/2 right there is 3.5, and 2 minus 3.5 would be a -1.5. It's just whether or not you want to put it in decimals or fractions that will make the difference there. So there's our p-value, and notice it has a negative on it because we are going to the left. That's going to work out really great. So now we have to be careful and remember that this is y minus k, and k is the y coordinate of our vertex, so that'll actually be y plus 3, the quantity squared. And then we need 4 times our nice little p-value there, that -3/2, that directed distance. And then we need x minus, and that will be our h value, 7/2. One last thing to clean up would be to go ahead and actually take 4 times a -3/2. So we will get y plus 3, the quantity squared, equals -6 times the quantity x minus 7/2. And there we have it. Now, let's make sure there wasn't anything else we were supposed to do with this problem. And it was just, we are writing an equation in standard form for the parabola that satisfies the given conditions. So, like I said before, your sketch of this is really helpful, and it'll help you to figure out what exactly it is that you need to do. You're understanding that the focus and the vertex are going to land on the same line. In this case, that line will be y equals -3. It is a horizontal line through -3. So there's that one. Now, next up, number 45. This is prove that the graph of the equation is an ellipse and then find its vertices, its foci, and eccentricity. Remember, we're not going to do eccentricity, so we're leaving that piece off. We just want to get a sense of, how do all of these conics work, and we don't need to go quite that far with it. So for 45, what you should notice is, hey, that is not my standard form ellipse that I had in section 8.2, and that's where this came from. So if that's the case, what I have to do is get my x terms together so that I'll be able to complete the square and get this to look like it should look. I need to get my y terms together. And I need to move that -23 over to the other side because it's not helpful right now. So now what? Well, I need to complete the square for my x's, so I am going to have to factor out, oops, I want to leave some space here. I'm going to have to factor out that 9 because the process of completing the square only works when you have a 1 in place for a in ax squared plus bx plus c. For my y's, I need to pull a 4 out. Factor that out, leaving some space. But as I have warned you previously, what I would do right at this point is remind myself about that 9 and that 4, because this is not going to work out pleasant if we forget that what we do to one side of this equation we have to do to the other. So let's complete the square over here with x squared minus 2x. B over 2 squared, -2 divided by 2 is -1, square it and you add 1. But we aren't just adding 1, we are adding 9 because 9 times 1 is 9. Now in the green one, we have another 2, except this is a positive 2. So 2 divided by 2 is 1. When you square it, you get 1. But again, we didn't just add 1, we just added 4 by doing that. So now we have 9 times the quantity x minus 1 squared plus 4 times the quantity y plus 1 squared. And that equals, well, 23 plus 9 is 32. 32 plus 4 is, ooh, nice number, 36. And now we know from experience we need to have this equal to 1. So we're going to divide everything by 36. And that will give us, by a little reducing here, 9 goes into itself once, into 36 4 times. And 4 goes into itself once and into 36 9 times. Oh, good grief. We know we need that to be a 1 by dividing by 36. All right, now, what to do? Well, let's go back and see all the good stuff that they wanted us to do. This was the first piece, and that was prove that the graph of the equation is an ellipse. We now have it in the right form. Now what we want to do is find its vertices, its foci, and we're not going to do eccentricity. So let me bring this down. Vertices and foci. Oh, come on, smartboard, behave. There we go. We know where the new center is because it is h and k. So that's going to be at 1, -1. We know that a, in this case, is 3. With ellipses, a is always the larger value. So if a squared is 9, that means that a is 3, and that makes this a vertical ellipse. All right, so let's get started. We've got a center at 1, -1. And we know that this is vertical, and it's going to go up and down 3 from there. So now we can answer the first part of their question, where are the new vertices? So we realize that when we were at 1, -1, and this became vertical, it's our y coordinates that are responsible for the up and down. So -1 plus 3 will give us 2. The first coordinate will just stay 1 because these are all going to line up on the major axis here. And then we'll have 1 and -1 minus 3, which will be 1, -4. for our vertices. And because we now know that, we also know that, of course, we need to put the foci on that same axis there, that same major axis. So that means we need to know where C is. Well, we don't have C, but we have a little formula. Since ellipses have a plus in their formula, we use subtraction to find anything that's missing. C squared is going to equal 9 minus 4 because that was our A squared and our B squared. So C squared equals 5, which makes C equal to, of course, the square root of 5. Now the exercise that we just did to find the vertices was really good for what we're going to need in order to figure out where we need to put C, because remember, we're still working with the y-coordinate here. We are adding and subtracting this to the y-coordinate. Now, if we want to graph it, square root of 5, 2.236. So we would need to go up about thus far and down thus far, if you want the visual right there. But we're going to do the same thing we did with the vertices. It's all about this -1 and adding and subtracting the square root of 5. So the foci are going to be at 1 and -1 plus or minus the square root of 5, and that is a perfect answer. So that's exactly how we want to leave that. Number 48, we have another ellipse here, and we want to group these together just like we did the last one. So let me get that so we can actually read those numbers. We would have 4x squared minus 32x, and then we'd need plus y squared plus 16y, and we'd move the 124 over. So this one we notice, hey, wait a minute, I don't have to factor anything out of that y squared business over there. I do need the 4 out of here. And that again is because when we're working with completing the square, we need to have a coefficient of 1 for a. And then we have plus y squared plus 16y, and we're not going to have to focus on, hey, what did I just add to this side? But here, definitely remind yourself, you know, that is definitely a point that, you know, people mess up, and then the rest of it doesn't make any sense, and it's the first place you go back and go, oh my goodness, I can't believe I did that. So we've got 4 times the quantity x squared minus 8x, and what we need to do is take b over 2 and square it. -8 divided by 2 is -4, and when you square it, you add 16. But we are really adding 4 times 16, which is 64. And then the y squared terms, we have 16 for b. 16 divided by 2 is 8. And 8 squared is 64. So we really added 64 to that side. So now we have 4 times the quantity x minus 4 squared, because this little 4 inside the parentheses always comes from b over 2 before we square it. So 4 times the quantity x minus 4 squared plus, well, this is going to be y plus 8 squared. And over here we have 64 and 64, which of course add to 128. So -124 plus 128 is going to give us a very lovely little 4. So what should we do next? We should divide. We're going to divide everything by 4 so that this equals 1. And that will give us x minus 4, the quantity squared, over 1. Now that 1 doesn't have to be there, but I want to make sure everybody understands that that's what our b squared value would be. Plus y plus 8, the quantity squared, over 4, which is beautiful, equals 1. All right, now we need to figure out the good stuff. We just proved that this, algebraically, we proved that this is an ellipse. So now it's a matter of figuring out, you know, what's going on here. So our center is at HK, which is going to be 4, -8. So there's our new center. And the larger of the two numbers, remember this is an ellipse thing only, the larger of our divisors here is always a. So a squared equals 4, which means a is 2. And because it is under the y position, that means this is vertical. So let's go ahead and get that on here. Oh, look at my graph here, it's separated. Not cool, smartboard. It did not take everything together. There we go. Alrighty, so we're at 4, -8. Ta-da! There's our center. And that last problem that we did, 45, really got us ready for this because we know this is vertical. That tells us we have to go up and down 2 units from that position to get our vertices. And that makes the math a little easier to think about because all you have to do is change the y's. So vertices for -8 minus 2 would be -10. And -8 plus 2 would be -6. So there are vertices. And again, that lines us up for those foci that we need. So c squared equals a squared minus b squared, because the formula for ellipses has a plus in it. To find something that's missing, we have to subtract. So c squared equals our lovely 4 minus 1. C squared equals 3, and c is plus or minus the square root of 3. So again, if you want the help with this visually, you're going to do, okay, the square root of 3 is about 1.7, blah, 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 and that will put us here and here. But we want that exact. And just like the vertices, we know that that's the y that we're making changes to. So here's the original y, and we need to add and subtract the square root of 3. So 4, -8, plus or minus the square root of 3. Let's see, anything else we needed for this bugger? No, 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 because we're not doing eccentricity. So, looking good. All right, next up, stuff from 8.3. So 8.3 was all about hyperbolas. And you can see that in number 14 because we have both the x squared and the y squared, but we have subtraction in between it there. So what we would want to do is think, is this horizontal or vertical? And the x squared is first here. It is x squared minus y squared, so that's going to give us a horizontal transverse axis. Again, you can think of it as the major axis. And a squared is 169, so means a is going to be 13, the square root of that. B squared is 144, so b is 12. Ugh, I might need to go by 2's on my graph here so we can get an accurate depiction. Or is this going to be too close anyway? I'm going to go by 2's. So our center for this one is at 0, 0. We don't see a minus h minus k, so we're at 0, 0 right now. And because this is horizontal, we need to go a units right and left. So we need to go 13 units, 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12, 13. And this just said sketch the graph of the hyperbola by hand, so we didn't necessarily have to label that. We certainly could, 13, 0 and -13, 0 as covertices when you're going through that. But this is a hyperbola, so we need to make a box with the dimensions that have been established by our A and B values. And then we need to make asymptotes. And then we need to remember, hey, this was going horizontal. So it's going to follow our asymptotes, but definitely going to go through that vertex point. And 15 is very similar. 15 is sketch the graph of the hyperbola by hand. Difference here is that we are no longer centering at 0, 0. We have an h and a k value. So our h value, because the formula itself is x minus h, our new center is actually going to be at -3, 1. So -3 and 1 is our center. And now we need to figure out if we're talking about horizontal or vertical. And notice it is x squared first and y squared second. And that's going to tell us that this is going to be horizontal. So this piece right here, it's all about which one is being subtracted. So when it's x squared term minus y squared term, then we have a horizontal hyperbola. All right, a squared is 16. So a is 4. And b squared is 4. So b is 2. Let's get a box made here. Our a value of 4 means we need to go right and left 4 units. And I'm just going to go by 1's on all of this. And our b of 2. Use those to create a rectangle, a box, whose diagonals, which should go through the center. Wow, did I get off there? There we go. Are the asymptotes. And we said this bugger was horizontal, so it's going to approach our asymptotes. It's going to hit our vertices, and ooh, I would want to fix that on my test. That looked like a big no-no. It looked like I crossed my asymptote. And there we are at. And again, you know, we could give all the coordinates for all the points here and give equations for the asymptotes, but they did not require that for this problem. Number 40 says find the center vertices and the foci of the hyperbola. So now it's given all that good stuff. I might do the asymptotes too. I kept thinking through the other two, hasn't asked for the asymptotes yet. So for number 40, our H and K center, -4, -6. So just starting to get some things visual here. And I'm going to label these vertices because in this particular problem they want us to find all that stuff. So having it labeled will help us out. X squared is first, so this is horizontal. It's x squared minus y squared. And a squared is 12. Ew. All right, so a is going to be the square root of 12. Which I know you could leave it like that. We wouldn't take points off, but that's just going to drive me bonkers. So I'm going to change that to 2 square roots of 3 by simplifying that one. All right, next up, b squared. Yuck. Is 13. So b is the square root of 13, but that's not simplifiable. So we'll just leave that there. All righty, we've got our center. We know this is horizontal. We have to go a units right and left. So we have to go 2 square roots of 3. So if you want the visual on this, you'll have to take 2 times the square root of 3 on your calculator, get 3.464, blah, 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 and we'll go 1, 2, 3.464. 1, 2, 3.464, right there. All right, now let's write coordinates for those vertices. When we put it on there visually like that, it helps us realize the x value, because these are lined up horizontally. The x value is what's going to change. So -4 plus or minus 2 square roots of 3 and -6 for our vertices. Now, they didn't ask for the covertices because, you know, we don't call them that when we do hyperbolas. Those are our semi-converse, or semi-conjugate. What we need to do here is think about where those foci are going to be at. And so that's our c squared equals a squared plus b squared. When we're talking about hyperbolas, there is subtraction in the formula. So to find anything that's missing, we use addition. So c squared is going to equal our a squared and b squared values of 12 and 13. And we say, hooray, at least one of these wasn't a nasty radical. Since that has to be on that horizontal axis, we think, okay, well, that's going to be the x-coordinate that's going to change. So we were at -4, but this one went perfectly. So -4 minus 5 was going to bring us to -9, -6. And then the other one, well, we were at -4 and we added 5, so we are at 1, -6. So let's see, did we give them all the things that we wanted to give them? We did, but like I said, I'm also going to go after those asymptotes. That's the reason I put that little square root of 13 business on there. And that's because I want you to see we really could think our way through those asymptote equations as we go through that. So asymptote, people get all weirded out by, you know, oh, I have to memorize this formula. No, you don't. I mean, as you're looking at this, you think from center to get to here. That would be what I need in order to write an equation for that asymptote. So you realize to go up, well, that was our semi-conjugate axis. So that was the square root of 13. And to go over, we had to go over according to what we had for our a value. You know, that's this distance over here. So that was our 2 square roots of 3. So if we want the slope of this, we're going to have plus or minus square root of 13 over 2 square roots of 3. And no, it's not beautiful, you know, but we talked about how we're not going to rationalize the denominator or any of that stuff anymore. And then we need our y minus k, so it'll be y plus 6 equals. And then we have x minus h, so this will be x minus 4. And to make it in the form that the book had, we just subtract the 6 from both sides. So y equals plus or minus the square root of 13 over 2 square roots of 3 times the quantity x minus 4 minus 6. And I'm trying to squish that in there, and it's not going very well. I was right, too big. And it would look like so. Again, they didn't ask for the asymptotes, but we certainly could find that, you know, just in case you have to do that on the test. Alrighty, number 50, graph the hyperbola, find its vertices, foci, and eccentricity. Not going to do that. Vertices and foci, yes. So we have 25y squared, and we're going to put the y term with that. And then we have negative 9x squared minus 54x, and we're going to move the 281 out of the way, just like we were doing for the ellipses earlier on the video. Because what we want to do is we want to group together the y squared pieces, group together the x squared pieces, so that when we're completing the square, all of that is staring us right in the face. So the y squared pieces, we could take a 25 out of that. And the x squared pieces, we could take a negative 9 out of that. We have to be careful though. You know, there's going to be some sign issues here because we're taking a negative 9 out. So be careful. As always, you could stop here and check. Negative 9 times x squared is negative 9x squared, and negative 9 times 6x is negative 54x, and then you're sure things are going well. But we can't forget about those numbers that are out in front when we complete the square. So with the green here, the y's, we have a b value of negative 2. Negative 2 divided by 2 is negative 1. When you square it, you get plus 1, but that is really adding 25 to that side. And then we have a b value in the x positions there of 6. 6 divided by 2 is 3. 3 squared is 9. But we did not add 9 because negative 9 times 9 is 81. And we subtracted negative 9 times 9 and negative 81. So now we have 25 times y minus 1, the quantity squared, minus 9 times x plus 3, the quantity squared, equals, and we realize that is 225. What a nice number over there. And now we also realize this is a hyperbola, which means we need this to equal 1. So we're going to have to do some division here by what seems like a huge number. But you can think of it as $2.25. You know, how many quarters would go into 225? And that's going to be a 9. And, well, then if we reduce this by 9, we're going to get 25. We're getting there. Things to notice. We now know where our center is at. But we have to be careful about it because we have to do x, then y. So that's going to be negative 3, positive 1 for the center of this one. And then we need to figure out our a and b. Well, remember, with hyperbolas, a squared is always under the first one. So this is vertical because y squared is first, but our a is going to end up being 3. And our b is going to end up being 5. So we can start getting some of this information on here so that we can give them everything they wanted, because way back up here we were to graph the hyperbola. So nice that they told us that. We could have figured that out on our own, but find its vertices and its foci. So let's get this on here. Oh, I did it again. Smartboard is having issues. It does not like me moving all of these things today. Up and down, up and down. It's saying, lady, pick one or the other. All right, negative 3, 1. There is our center. And it is vertical. We have to go 3 units vertically. So up 3 and down 3. And we could certainly stop and tell them what those points are. And that's because we realize it's the y coordinate that's going to be affected by that 3. So this will be negative 3 and 1 minus 3. And then we have negative 3 and 1 plus 3. You could count it too at this point. It doesn't matter. So there are those vertices that we needed. And then we're going to use B to go out in the right and left direction. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So those are, yeah, we think of them as covertices, but are semi-conjugates there. Then we still need the foci. So we go ahead and say, alrighty, foci, come here. C squared equals A squared plus B squared. The formula for hyperbola has subtraction in it, so we use addition to find anything that's missing. C squared equals 9 plus 25. C squared equals, yuck, 34. C is the square root of 34, but no biggie. You know, we know this is vertical, so we know we're going up and down the square root of 34, and if you really wanted to have that visual, you could say, it's about 5.831 up and down from the center. And that, again, just reassures you, oh yeah, this is going to be just like the vertices there. I need to add and subtract this to the y. So the foci are going to be negative 3 and then 1 plus or minus the square root of 34. All right. Make sure I did everything they said to do. Well, I didn't finish graphing it yet, but graph the hyperbola, find its vertices and foci. Yeah, I've got that. So what I need to do is make my little box and get this on here. And the box is, of course, made up of those, well, vertex and co-vertex points. And hyperbolas wrap around these foci. Beautiful. So there we have it. All the info they wanted, do we have it all there? We have the center. They didn't necessarily even want that, but we've got our vertices at negative 3, negative 2, and negative 3, 4. And we have our foci at negative 3, 1 plus or minus the square root of 34. And we have it graphed. That's what we needed to do. All right, our fabulous problems that we ended at on your review sheet. You know, just trying to put some wordy problem stuff together. One of the moons of Pluto. Okay, so I'm going to start here. If it is a moon of Pluto, we can think of Pluto as our 0, 0 here. It says it's in an elliptical orbit around the dwarf planet. Pluto is approximately a sphere. You know, in real life, nothing's ever perfect. It has a radius of 1,151 kilometers. So this right here, going in any direction, is 1,151 kilometers. Charon is in orbit about the planet 960 kilometers above it at its farthest orbital position. So I'm just going to go above right here. And 920 kilometers above it at its closest orbital position. Well, if it's an elliptical, then that would mean that this is going to be 920 kilometers over here. So this is not really 960, 0 up there. That's why I'm labeling that 960 kilometers. And this is the 920. So I'm not making points out of this. What I'm doing is getting a visual of what this is, what it's going to look like. All right, And for this one, I just used the 960 as the largest number going above it, so that would make this a vertical ellipse. Now you might have drawn it the other way, and that's perfectly fine. I mean, it's space. Which way do you want to be up and which way do you want it to be down? But notice I drew my Cartesian coordinate plane here to my advantage because I have my center at 0, 0. This is going to be a vertical ellipse, which will mean that I'm going to have to use for this one, I'll have to use the fact that if I want this vertically, I'm going to have an x squared and a y squared, but my a squared and b squared are going to be turned around. So this will be a b squared and this will be an a squared position here. Now, like I said, you wouldn't have to do that. You could certainly turn these two pieces around, and your book likes to switch the x squared and the y squared position. Maybe I'll just go ahead and do that. All right, so if we stick with what the book has been doing, we know that the difference here with this ellipse is because the biggest number that I was using there was adding and subtracting 960. That is needing that y squared to be first because this would be vertical. All right, so now I need to figure out what a is. Well, if the radius of Pluto is 1,151 kilometers, that is the radius no matter where you are at. So this is also 1,151 kilometers. So if I want to figure out A, and obviously this is not to scale, I need to take 1,151 and I need to add 960 to it. And that gives me from the center 2,111. So I'm going to need y squared over 2,111 squared. And I need to go after b squared the same way. So I've still got 1,151, but I need to add 920. And that gives me 2,071 all the way to the center here. Actually, I should just put it right there. So that'll be 2,071 squared equals 1. Now these are larger numbers, so we could certainly just leave it like that. But the key to this is going to be that your sketch has to match your equation. Because mine was vertically oriented, I needed to make sure that I had a vertical ellipse formula for that. Those things have to match. If you went the other way, well, your sketch needs to show that. Your sketch needs to show, hey, I put the 960 out here and I put the 920 out here. And then it would be horizontal. So then you'd have x squared over a squared plus y squared over b squared. Same thing with this one. So we've got scientists hoping to place a satellite in an elliptical orbit above the planet Mercury. All right, Mercury, you're going right here. That's where Mercury's going to go. The radius of Mercury is 2,440 kilometers, so that is 2,440 kilometers. And it says determine the equation for the satellite's orbit if it is to be 567 kilometers at its closest orbital position. Well, I'm going to put that here this time. And 620 kilometers at its farthest location. So this would be 620 kilometers. Now notice that this time my smaller value of 567 is above and my larger value is horizontal. So that means I should be using x squared over a squared plus y squared over b squared equals 1. And I just need to figure out again what my a squared and b squared values are. So for a squared, I have 620 plus, again, that radius, we're going to say it's almost a sphere. So we're just going to use 2,440 to approximate that, plus 620, which is going to give me 3,060 squared. And our b value, well, 2,440 plus 567. And that is 3,007. Right there. Now we need it to equal 1 because it's an ellipse. Again, your sketch must match your drawing. I had that 620 value, which was the larger value, horizontal. That was horizontal in my drawing, and so my equation had to match the fact that that was going to be horizontal. I needed to have x squared over a squared in order for that to match. So that's what you have to make sure happens too. Your drawing matches your equation.